Okay, welcome, EE123, lecture 17. Woo! Oh, no. Well, we gotta make it. EE123, lecture 17. Woo! Okay. Morning. That's great. It's a good start. It's a Wednesday. Okay, last time we talked about changing sampling rate via discrete signal, digital signal processing. We talked about upsampling. We talked about downsampling. We talked about rational resampling. And we saw that there's, what, the elevator was stuck? Who's taking the elevator in Corey? Let me advise you against taking the elevator, Corey. Elevator, Corey, while being new, still gets stuck sometime. And if you want to get somewhere and also be healthy, take the stairs. I really recommend that. Give you an example of one of our dearest faculty, Professor Laura Waller, who was on her way to class and wanted to, get there fast. She took the elevator. And then 30 minutes later, she texts her class, as she sends an email to the class, well, class is canceled today because I'm still stuck in the elevator. Okay, so one thing we identified that there is a problem when you want to do this rational resampling is that if we're going to resample, let's say by a ratio which is, 1.01 or 1.00001, then we're going to have a problem because we are going to do so much computation, need so much memory, it doesn't make sense if we just need to change our rate by that low. And so today we're going to talk about how we can get rid of this extra computation by not computing stuff that we're going to be throwing away. Because when you do decimation or upsampling, there's a lot of zeros that are associated with this. And so we don't want to compute them. So we're going to talk about that. Before this, I want to talk about, and this is called polyphase decomposition. It's a strong name for a simple approach, but it's also called multi-rate processing. And so performing different DSP operation at different sampling rates. That's really what multi-rate processing really means. So if you want to operate on different bands of frequencies, you can then decimate the signal or downsample the signal because you're going to represent at a smaller bandwidth. So that is what we're going to talk about today. Before this, I want to talk about Lab 3. Who has not started Lab 3 yet? Like at all? Not even the part 1? You should start very quickly because part 2 takes longer. Okay, so if part 1 takes you long, part 1 is I have to say it's pretty straightforward. Part 2 is pretty straightforward if you've done it before. Okay. Hence, you have to do it because it's not necessarily as straightforward. Okay, but it's one of the coolest labs in this class. There's 6 cool labs, and this is one of them. Okay, and all of them are really cool. But this one is really, really nice. You'll get to hear stuff too. Okay, so part 1 talks about, again, spectrograms. And we talked about this in class, and this is just a way to go and realize this. So there are functions in Python, MATLAB, all of these do compute spectrograms for you. But you're not going to use those. You're going to compute them yourself. Okay, so you're going to write functions that will compute spectrograms with and without windowing and see the result of this particular signal that you saw before. Then you're going to do this computation with overlapping windows. And we gave you a hint how not to use for loops. Okay, did we post that? Is it posted on Piazza? Yeah, how to not to do for loops. And the truth is, if you're programming stuff in C or like really efficient assembly, I don't know what then of course you're going to do loops. But a lot of signal processing is happening today is done on a higher level languages like Python and others. And so there, doing vector type of processing is really important if you want to maintain efficiency. Because once you have a vector processing, then you go and you call a routine that does an efficient implementation. If you're doing for loops in Python, this is the most terrible thing that you would be doing in terms of your efficiency. So this is one of the aspects of doing that type of a computation, and how to do it fast, so on and so forth. Okay. So you're going to compute the spectrogram overlapping window. You're going to see like a nicer looking spectrogram. And then you're going to look at different temporal frequency resolution trade-offs with the size of the window. And this is all reproducing what I showed you in class. Okay, so this is the first part. The reason that we also want you to write an efficient spectrogram is because the second part, you're going to do a spectrogram of large data set, like a relatively large data set, and it will just take you a long time to process it. Some computers may not handle it. Okay, so that's the other thing. If you sample at 2.4 megasamples per second, and you're requiring 10 seconds, that's already 24 megabytes. No, more. It's 24 times at least 4. But it's complex data, so times 8. So it's like a 100 megabyte data set that you're going to be operating on. And that's for just 10 seconds. So efficient computation is really important. By the way, and that's why multi-rate processing is also important. If you're going to take only 200 kilohertz out of this 2.4 megahertz, absolutely you can reduce the computation significantly by doing operation like downsampling, filtering, things like that. What we're going to do is you're going to look at broadcast FM radio, and in particular KPFA station, which is our own Berkeley KPFA free speech station. It's up above Claremont Hotel, up on the hill. So it's located very nicely up here. This is the university. That's the university, right? Or Clark Hare, I think. No. Oh, no, that's us. Okay. So it's located up here. It transmits at 59 kilowatt effective radiation power, which probably means that they have about a 6 kilowatt transmitter. So it's pretty intense. So you should get good SNR, even in your inside a room, though I would say if you're in a basement, not so good. Okay, so again, like every other place, please do things closer to a window outside because that's where things are being transmitted. Especially if you're going to use the small antennas that we give you, they're not that efficient for FM. FM wavelength is 3 meters. This is not a half wavelength antenna or quarter wavelength antenna. Okay, so they're much smaller, so they're not as efficient. Okay, so what is FM modulation? FM modulation, or that particular station, what it does, it takes a signal that looks like this. It's actually composed of several signals that they want to transmit. On the baseband, it transmits the left plus right channels. Okay, so if you want to transmit stereo, that will be the mono part of a stereo. Okay, so if you have a stereo signal, you take the left channel, you take the right channel, you add them together, and they transmit on the baseband. That's not modulated. Then they transmit a pilot signal at 19 kilohertz. Okay, this is just a pure frequency at 19 kilohertz. That pure frequency is the same one that's modulating using amplitude modulation, the left minus right channel. Okay, so if you want to get stereo, if you have the left plus right and the left minus right, if you add them together, you get the left. If you subtract them, you get the right. Right? So if you demodulate both somehow, then you can get yourself the right stereo. So at 38 kilohertz, so that's twice that frequency, this is amplitude modulation of the left minus right channel. Okay? It's amplitude modulation, but it's what's called with a coherent receiver and transmitter. There is no 1 plus cosine, as usually is done with AM. This is without the 1 plus. If you don't have the 1 plus, if you want to demodulate this, you need to demodulate with a cosine. If you demodulate with a sine, 90-degree phase, like a 90-degree phase shift, you'll get 0. So you have to know exactly what the phase is to do this. And that's why they send this tone, which you can then use this as a phase reference to figure out what is this, because this is exactly twice the frequency, same phase. Okay, that's why it's sent. We're not going to do this, okay, in this lab. It's something that you could do yourself, but we're not going to do it. I was going to do it. The lab is long enough, and you got other stuff going on. Okay. Well, I mean, yeah. So that's exactly. So we've been considerate. We've been considerate. All right. Then, at 3 times that pilot frequency, they're going to send RBDS, which is digital data. Again, we're not going to demodulate that. And that gives you the station information, things like this. And then at 67.65 and 92 kilohertz, there are subcarriers, which are actually subsidiary channels that KPFA is transmitting for some Punjabi radio and Haitian radio stations. They used to be, a while back, used for playing music in department stores, elevators. You know, they'll just have that. And so you'll have a radio inside those elevators that would basically demodulate that. And it's kind of low quality, 10 kilohertz bandwidth type of FM modulated. And I'm going to talk about this. Okay, so this is a spectrum of the baseband. That's what they want to transmit. How they transmit this is they do an F frequency modulation. So that signal here, that's X of T, which is composed of a few signals, is then frequency modulated. Okay? So it's going to change the frequency of a carrier at a particular center frequency. So around 94.1 megahertz, you're going to have frequency deviations that are dependent on that signal. And the way that you write this is you write it as an integral over that signal. If this is normalized to between -1 and 1, then you've got deviation of about delta F in frequency. Okay, plus and minus delta F pretty much in frequency. You're going to be modulating. Okay, if you integrate over this. If I take the derivative of that, this is the phase. If I take the derivative of the phase, I get the frequency. So I'm going to get FC, and I'm going to get delta F times XT. Okay, that's the derivative, which is exactly the signal that I want. So the derivative of the phase is how really you demodulate FM. You need to take the derivative of the phase. If you take the derivative of the phase, you'll get a signal that has a spectrum like that. It's kind of like, right, strange, but factual. And you're going to be seeing it. Okay, so what you're going to do then is you're going to capture like 1 second. And the reason that you capture only 1 second first is because computer spectrogram of 10 seconds is computer spectrogram over 10 megabyte. It's too much. Even that takes a little bit. So first of all, you're going to capture 1 second at 2.4 megasamples per second. Okay, complex megasamples per second. Okay, and you're going to plot the spectrogram. And when you plot the spectrogram, you see that around 94.1, there is really a station that looks FM modulated. It's frequency modulated. There's frequency changes over time. You're going to also see some other channels. Now, why this is brighter? Because this is a 59 kilowatt effective radiation power that's just next to you. Okay, that's why it's so strong. The other ones might be strong or not, depending on your position. But there might be one station here, and there's another station here that you can barely see because this was captured in the East Bay, like in the other side of the hill. But on this side of the hill, these are stronger. Okay? So you're going to see this, and it says, okay, great. Okay, we look at this. That's fantastic. But there's a lot of stuff over here. We really want to just process that station. Right? So you need to get rid of, first of all, a lot of noise in the spectrum outside, and also other stations that interfere. If I try to demodulate this, the other stations are going to be interfering. So what do I need to do? How do I get rid of the other stations and noise? Filter. Actually, it's a low-pass filter because that is actually zero frequency. Right? Because I chose my RTL-SDR to have a center frequency of 94.1, which means that this is really the zero frequency of the signal that I captured. Okay? So it's really just a low-pass filter. And the bandwidth of FM stations are 200 kilohertz. So I'm going to do it, and you're going to design it very simply. You're going to do this. So first of all, you're going to design a filter which has 513 taps. It's actually, the order of it is 512, and we'll differentiate that when we talk about filter design. The order is called 512. The length of the filter is actually, how many coefficient it has is actually 513. MATLAB, if you want to design something, you have to specify 512. In Python, you have to specify 513. They'll give you the same filter. Okay, so there's some nuances that you have to think. It's going to have a cutoff frequency of 100 kilohertz out of a Nyquist frequency, which is 2.4 megahertz over 2. Because the highest frequency, when you sample at 2.4 megahertz, is 1.2 megahertz. So again, all this you have to figure out. And it uses this method of basically creating a sink and windowing it with the Hanning window. Okay? That's how it's doing. It's a sink that's windowed by a Hanning window that gives you that low-pass filter. You're going to be filtering it, and once you filter, look how nicely it goes around the station. But now I have a band-limited signal. It's wasteful. Now I can downsample it. And I'm going to downsample it by a factor of 10. Am I going to get aliasing? If I downsample it by a factor of 10? Decimate by a factor of 10? No, this is 200 megahertz bandwidth. The whole thing is 2.4 megahertz. This is 200 kilohertz. The whole thing is 2.4 megahertz. If I decimate by a factor of 10, my bandwidth is going to be 240 kilohertz, which is more. I'm not going to get aliasing. This is exactly the downsampling that we talked last time, low-pass filter and decimation. Right? So low-pass filter and decimation, I get then a spectrogram that looks like this. Now this goes from minus pi to pi. You know, the whole station from minus 128 kilohertz to plus 128 kilohertz will then be minus pi to pi. If I take the DTFT, I get that. It's exactly like we saw last time. If I didn't take the low pass, I would get aliasing. And because I low passed actually to 200 kilohertz, not 240, on the band edges, I see zeros. You know, it looks black. Because I did narrower than I would actually sample it. And that's fine. Okay? So I could have sampled it by a factor of 6, for example. And it would still not give me aliasing. But the roll-off of the filter would maybe alias a little bit, like I showed you with the SDR. Okay? So all these things, again, you'll see make more sense. So then you're going to do this. Look at the spectrum. It looks FM modulated. That's great. Okay? Now you're going to recapture a signal again for 10 seconds. And you're going to go through this processing without displaying this. After the filtering and decimation, then you'll display 10 seconds of that. That's okay. That's 10 seconds at 240 kilohertz. You know, computation is not too bad. 10 seconds at 2.4 megahertz is pretty intense. Okay, so you display the spectrogram pretty quickly. Then any questions up here? So this is really related to what we did exactly last time, right? Low pass, decimation, that's downsampling. Now the rate that our samples after we did this is 240 kilohertz. Questions? You did sequentially. So in fact, when you filtered at 2.4 megahertz, and then you downsampled after that. So it was not efficient as we will learn today, but it's still the operation of decimation. We'll get to that. Okay. So now you're going to demodulate the FM signal to get X of t. And how are you going to do this? Who's in my ham radio class? Great. The rest of you either know ham radio a little bit or should learn that till the 16th. Okay? And when we talked about FM radios, FM modulation and demodulation, I described, what's in an FM radio. How do you demodulate this? And there's two components there that one of them is called a limiter, and the other one is called a discriminator. Okay? The limiter will remove unwanted amplitude variation. So after you downsample, filtered, decimated, effectively downsampled, there's still amplitude modulation existing in the signal just because of fading, various interferences, lots of propagation issues. There's always going to be amplitude modulation, amplitude deviations. We want to remove this. We want the signal to be constant amplitude, but have all the variations happen in the phase, in the frequency. So the limiter is the things that does that. And how do you do a limiter in hardware? It's more complicated. Like you have to kind of bound the signal so it doesn't go above a certain range, things like this. In DSP, it's as simple as dividing by its absolute value. Okay? That's the limiter. You divide by the absolute value, and then you only get the phase variation. Now you've got a normalized signal that's normalized in magnitude to 1, but it only has phase variation. That's it. Divide by the absolute. Now, if you divide by absolute, maybe there was a chance that something went to 0, then you got yourself, a problem numerically. So you're going to divide by the absolute value plus some epsilon, just to make sure that you don't have this effect. Okay? So this is really the amplitude of the signal, and you see because of noise and other things, it has deviations. And you're going to remove that. Great. Next step is discriminator. The discriminator, what it does, it takes frequency deviations and translates into amplitude deviations, which is effectively demodulation. So any frequency deviation, you want to see that as amplitude. There's many ways of implementing this in DSP. You can use a phase lock loop. There's just like almost infinite number of ways that you can do this. The one way we're going to do this is using this relationship. If I take a time derivative of my signal, okay, just compute a time derivative of my signal, and then multiply by the conjugate of my signal. If you stare at this long enough, what is the time derivative of your signal? If your signal is e to the j, whatever, what's FM modulated, the time derivative of your signal is 2 pi j delta f times xt. That was in the exponent. And then the signal itself, right? Because that's the derivative of an exponent is the same thing, right? So then it's e to the j 2 pi delta f, so on and so forth. So you've got now some amplitude modulation, so amplitude deviation, as well as frequency deviations after taking the derivative. Then you multiply by the conjugate. When I multiply by the conjugate, all the phase stuff goes away. The phase of the conjugate cancels the phase here. And so the only thing I'm left with is 2 pi j delta f times xt, which is my signal. That's really my demodulation. Except that it shows up in the imaginary channel, as imaginary value. But then you just take the result dot imag, and now it's a real number. Okay. So that's the thing that you need to implement in order to do the demodulation. Now it only works if you pass it through a limiter. Because if you take a derivative and you don't have a limiter, then it's going to be affected by the amplitude changes as well. Okay, so that's why we do a limiter first. We remove the amplitude, so now everything goes to this. Any questions? How do you take a derivative? That could be a question. How do you take a derivative? Finite difference could work. Could work. If you take a finite difference, if you look at the DTFT of a finite difference, it looks like a derivative in the low frequencies, but it rolls off in the high frequencies. So the Fourier transform of a derivative is basically a linear function in the frequency domain. So finite differences actually rolls off. And it's okay if the bandwidth of the FM was narrow, but this is a wide band FM. We actually have stuff in the high frequencies that needs to be differentiated, especially the subcarriers are high frequency. And so that's not going to work that well. Okay? So finite differences is one, but you can actually create a differentiator filter that has a frequency response, which is linear in frequency. And that's exactly what we're going to do. Okay? You're going to use a function that implements the Parks-McClellan algorithm, which is also called the Remez exchange algorithm, which does an optimal filter design that, based on specification, it will give you the equi-ripple over frequency. So the ripple across the frequency deviation is going to be the same everywhere where you design. It's kind of a minimum maximum implementation. So you minimize the maximum deviation from the desired filter. We're not going to talk about right now, but we're going to talk about it a little bit later in class. But all it does really is you call this function, which we're going to have an order of 31, and you're going to specify from 0 to 105 kilohertz, I want to have an amplitude that's varying up to 1.05 over 1.2. So basically, it's a linear function. You have to tell that it's a differentiator that knows to make it linear. And then I want it at the edge of the band, I want it to be 0. So at the edge of the band, I want it to be 0. That's the 0 over here. And so the specification is really, I want the filter to look like this with some ripple around it. I don't care what's going on here, but I want it to be 0 at the end. Now, why do I want it to be 0 at the end? As it turns out, if you have an asymmetric frequency response, it's also going to be an asymmetric filter. And if it has an order of 31, which is an odd order, it has to end up with a 0 at the Nyquist frequency. It has to. It's not possible not to. Well, we're going to talk about this when we get to there. But it's not possible to design a filter which ends up at non-zero. For that kind of order, now why do we use this order? Because that allows us, when we do the convolution, to have 0 delay, or an integer delay of our filter signal. Okay, so it's not a 0 delay, it's an integer delay, which we then going to compensate for. Because when you do the differentiation, I need to multiply by the exact same phase of the conjugate. If this part is delayed, that's not going to work. I need to know how much exactly the delay is, and it's much easier if the delay is integer. And that's why I'm using an odd size filter. Okay, so all of these details, but really important. Okay. So you're going to design this differentiator. It's going to look something like that. And it, these two looks like a finite difference, but there's, other stuff that makes it. And then its amplitude frequency response is linear. This is the absolute value. It's linear over the range that we're interested, up to 100 kilohertz. And then it drops down to 0. Okay, so that's great. Now you're going to convolve. When you're going to convolve, in order to compensate for that delay that you have in the filter, you're going to use FFT convolve with a modification which is called same. So you keep the same size after that. When you do that, then it shifts your signal such that it's not delayed. Okay? So if you do that over a chunk, it will, after convolution, it will be delayed by 16 samples, as it turns out, and then it just moves it back. It does that for you. Okay? So then you're going to do this, and you're going to implement the demodulation, and it's going to look like it's going to look like that. When you display the spectrogram, first of all, the spectrogram is going to be real. Right? It's a real signal. After you demodulate, everything goes to the imaginary channel, so it's a real valued signal. Everything. It's a real if you just take the imaginary part. Right? So that is a spectrogram. And look, it looks exactly like the spectrum that you see here. There's the left plus right, the 19 kilohertz, the left minus right. This was speech, so there's not much stereo, so the signal in the stereo is low. RBDS is hard to see. It's there, but it's kind of hard. It's a weak signal. It's 0.05 of the, so it's 20 times lower in amplitude than the rest. And then the two subcarriers. Okay, so you see here. These are the two subcarriers. These look like FM stations. It's kind of weird, right? They look like FM stations now. We'll get to that. Okay, so now you've got this, and you want to play just the left plus right. What do? How do you play just that part of the spectrum? I've got a 240 kilohertz bandwidth signal, and I want to play only up to 16 kilohertz. What do? Low pass, and can I just send it to the speaker? Can I send it to my my audio at 240 kilohertz? I can't. So we're going to downsample down to 48 kilohertz, which our speakers can play. How much? Factor of 5. Do I get aliasing? No. And it's going to look like that. So low pass filter, decimated by 5, and so now the peak signal goes up to 16 kilohertz. Maximum frequency is 24 kilohertz. Okay, and I've got all this black stuff here, which because I filtered up to 16.
Nieta. The name of the CD is Canto America, and we're going to listen to the Mobile Santa Maria classic Afro Blue. And what can I say about this one? Just absolutely.
Okay, that was the 10 seconds. Okay, so now the next step will be to demodulate the subcarriers. Okay, so that's the next step. To demodulate the subcarriers, we already did this part. We got to the discriminator, and then we ended up with a spectrum. We want to then decimate the subcarriers. Now you can think of it as like these matryoshka, I don't know how you pronounce it, dolls, like the Russian dolls, where you unfold one level and then you get yourself another FM in it that you then need to kind of open again. So it's like an encoding inside of an encoding. Okay, so FM inside of FM. So we need now to do, again, an FM radio implementation. We need to then demodulate one of those subcarriers to the baseband, which the SDR did that for us before. Now we have to do it ourselves. So you're going to be demodulating by some frequency, the subcarrier frequency, low-pass filter, decimate, then implement a limiter discriminator, then low-pass filter again, and then play it. Okay? So basically another FM radio after that. Okay? It's the same as this FM radio. Okay? Another FM radio. So it's two FM radios implemented inside each other. Okay, so if this is the one single-sided spectrum, because this was real, I'm going to complex modulate it by the carrier frequency, by the subcarrier frequency. When I complex demodulate by 67 point whatever frequency it was, I'm going to get now a complex spectrum. Okay, so I'm going to display now a two-sided spectrum in which this shows up in the middle at 0. Right? It shifts the whole spectrum. Really, I mean, it's a two-sided thing, right? But it was just a mirror of it. When I do demodulation by e to the 2 pi j, whatever frequency is, it kind of circularly shifts it. And you see the circular shift here, right? Circular shift. This was about 0 before. Now it moved down here. That's the 19 kilohertz, and that's the minus 19 kilohertz. They just shifted down here. And because they shifted down here, the subcarriers now are at 0. And that's the negative subcarrier. Yeah. Okay, so now we have the subcarrier here, and we want to then FM demodulate it. Now it looks exactly like the case that we had when we captured the original data from the SDR. Right? We have an FM station exactly on 0. What do you do then? You low-pass filter, you decimate. Now it's 48 kilohertz bandwidth. And now I'm this looks like an FM signal. What I'm going to do now, I'm going to pass it through a limiter discriminator again. So you need to design a new filter because now the sampling rate is 48 kilohertz. Before we had a filter for 240. So we have to design a new filter that is adjusted to that sampling rate with the right bandwidth. Okay, so it's a new filter. You're going to demodulate? I didn't amplify it enough. Sorry. But this guy was speaking French with a Haitian accent. And the voice quality was much poorer because it's only 10 kilohertz bandwidth. It's not the nice 16 kilohertz. It's 5 kilohertz in each side, whereas FM, broadcast FM is 16 kilohertz in each side. Okay, so it's much poorer quality. But you're going to be hearing, it's like AM stations, kind of. You know, it's not very high audio quality. But you're going to be able to hear it, and that's, you know, you're going to filter it down to 5 kilohertz maximum frequency, and then you're going to play it. Now, because of the dynamic range of the SDR, there's going to be some interference between the main station and those subcarriers. So the subcarriers as 92 kilohertz is going to even sound a little bit poorer because of the interference. There's not enough bits there to resolve the right, you know, the accurate angle. So that shows up as some interference that leaks. But at the 67 one should be actually really good, reasonably good quality compared to what you can achieve. Okay? Any questions? What? That station pays KPFA to put that station there for, I guess, the Haitian population in the Bay Area, or people from Punjab. There you go. Do you listen to this?
No, never heard of it, but I'm excited.
Yeah.
So 5 kilohertz, why is that not enough to give you like high quality audio? Because like when I talk, I'm sure I only use like 2 kilohertz of bandwidth.
No, really. The majority of the amplitude is in the 2.5 kilohertz. But it sounds like talking on like old phones because they would filter up to 5 kilohertz. Yeah, it doesn't capture so it reduces the quality. So music doesn't sound as nice, right?
Well, like music goes into like higher.
Right, but even audio, you still have, your voice actually, it's really, if you think what it is, it's really impulses. It's a strain of impulses, right? So that's what your vocal cord do, and if you filter it, then you cut off some of them, so it doesn't sound as good. It's going to be more noisy as well, right? Because it's in the high frequency, it's lower, so it's not going to be a great quality, but it's going to be okay. Yeah.
When FM stations purchase spectrum from the FCC, do they have to buy the subscription?
No. So it's not, because it's already within the bandwidth. So as long as it doesn't interfere with the main station, then they can do it. It's not regulated, that part. In Europe, sometimes they'll transmit data there to, for a bus station arrival. So bus stations will have a receiver, and then they'll just, get the arrival from that. Yeah, for this one, you need a custom radio. You can buy for $30, I think, $40. You can order a special radio that can do subcarriers. There's not a lot of these kind of radios, but you can still buy them. Okay, so this is going to be, I think, a really fun lab to go through. And if I challenge you if somebody can actually make it continuous. Okay? It doesn't have to be real time. It could be delayed, but continuous play. And it's not easy. There's tricks with the SDR that you need to do. You have to use callback functions and things like this. So the SDR in the background keeps on receiving samples. So if anybody does that, they'll get extra credit. Okay. And then it'll just keep on playing, without stop. You also need to think about the edges of the, if you acquire 10 seconds of a chunk. The thing is with Python, if you give it chunks of like half a second, it might not be quick enough to finish it in half a second. But if you give it chunks of 10 seconds, it might finish processing them in 5. So that's enough to do continuous play. But you have to take care of the edges between the chunks. When you filter and things like this. So it's not trivial, but it's not hard. But we'll give you, if you do that, you'll get extra credit because that's significant. We didn't want you to do this though. So, we didn't want to, because you're busy with other stuff, right? Too. Okay, so I spent a lot of this lecture on this lab, which is great. I did want to cover other stuff too. So before we move on to the other stuff, any more questions about the lab? Because I really enjoy. It was fun making it. This is the third time we're doing this. We still spent about 10 or 15 hours improving it. So. I hope there's less bugs and it's more clear. All right. Okay, so let's go back to resampling. And resampling is important. Resampling is important because there's a lot of systems that have, different clocks and different, you think that you're sampling at a certain rate, but you're actually not sampling at that rate. You need to resample your signal to really get to that rate, and so on and so forth. And you can do that in a digital domain. So it's really, really useful to be able to do these. Also, changing rates is, as you've seen, it's going down sampling, up sampling. They're all very useful when you want to interface to hardware that can only accept that kind of rates, and so on and so forth. But if, let's say, I want to do something like resample by 1.01 because I have a clock drift of 1%, then what do I do? According to last lecture, you need to expand by a factor of 100, then filter by pi over 100, which is really expensive if you think about this, because now if you want to do a filter for a high sample rate, you need more taps. It needs more coefficients in order to be a sharp filter. Okay, so that filter is going to be applied to the higher rate. It's really expensive. And then, after you did all of that, you're going to throw all of it away. Most of it, you're going to just oh, I computed you? Go away. I don't need you. Computed that part. Good okay, stay. Right? It's why spend all this time computing stuff that we don't need? Okay? Right? Because I'm going to downsample by 101. So I'm going to take every 101 sample. The rest, don't care. Go away. In this class, I would take John and that's it. Right? All of you will just... Okay. In 61C, only 7 students left. 61A, 14. But that's it.
You did great.
What? You did great. Yeah. Okay. So fortunately, there's a way to go around it, because if we're going to compute stuff that we're going to collect, let's not compute it. Okay, that's the idea. And so it's all based on the ability to interchange operation of expanders and compressors with filtering. Okay? So if you look at an expander and a compressor, they're not LTI systems. Right? Now the question is, if I have X of n, coming in, goes through some system, and then I'm going to upsample. Is it the same as first upsampling and then filtering with that system? And the answer should be not really. Depends. And so let's look at this. If I filter with H is Z, then I get H e to j omega times x in the frequency domain. Right? You just multiply their frequency responses. Then you're going to upsample. What happens when you upsample? Not upsample, expand. You compress the frequency, right? You compress the frequency, and you compress the frequency of both. Okay? So now everything there will be multiplied by L. Okay? Now what happens here? If I expand this, the transfer function, the spectrum is going to be x e to j omega times L. That is going to be compressed. But then it's going to be multiplied by H of Z, which is not the same as this. Does this make sense? Great. But we can make them the same if we instead filter it by Hz to the power of L with a compressed version of that filter, right? So we could potentially change those if we just filter that system with a modified system. And so they're not equivalent, but if I upsample by a factor of L and then filter with Hz to the power of L, then I will get exactly the same thing. Okay? So if I exchange the filtering with an expander, I can do that if I take my system and compress it in the frequency domain by a factor of L. Or in fact, expand my system. And it kind of makes sense. What it does really, it expands your system too. Okay, so you know what the system is, you just expand it as well. And so everything should fall down in the right place. Okay, so this is filtering followed by an expander. The question is, if I have an expander followed by filtering, can I then interchange them? So it's not the same thing. So if I have an expander followed by a filter, so that's the opposite. Now I want to go, can I do H z to the 1 over L and then expand? Can I do that? Can you?
Depends on what the frequency response is for H of Z.
Okay, what will be then the criteria?
If it expands too far and starts arising, then
So what I do here is I expand it, right? Expand, like stretch the frequency, right? Stretch the frequency. This is only be true, that is be true, if H of Z is irrational. It's going to be rational. That means that H of Z is going to be rational only if it was expanded before. Okay, if it has zeros in between, then I can compress it, which will expand in frequency. But that comes down to exactly the same thing that you're saying. Yeah, so it doesn't actually alias afterwards. That's right. So if H of Z is rational, which means that it's actually going to be a result of an expansion. It's going to have zeros in between samples. Then I can exchange that. But otherwise, it's not possible. Okay? All right. So I'm going to finish here because I ran out of time. Next time we're going to talk about more. We're going to talk about what happens when you do a compressor. What can you interchange those? And then we're going to say, well, wait a second. I'm going to have this filtering operation. And I'm going to be decimating afterwards. So filter and decimation. Can I first decimate and then filter? And the answer is going to be probably not. But can I take my filter and decompose it into smaller filters or different filters such that then I can replace the decimation with a filtering operation? And then the answer is actually going to be yes. And so what we're going to do then is what's called a polyphase decomposition, where we're going to break our filter into several smaller filters that can be exchanged. And then we're going to perform that operation using those filters and then combine the result afterwards. Hence, not computing stuff that we're going to be throwing away. Okay? So that's the idea next time. I guess it's going to be Friday. And don't freak me out by not showing up. Like, till the last minute. Because we had, like, one person when I showed up. Freaks me out. All right, see you.